Okay, welcome back. In this video, we're talking about phase diagrams, and the two big ideas that are going to lead us is that a phase of a substance is determined by the distances between the particles and the motions of the particles in that substance. That's how we tell the difference between a solid, a liquid, and a gas. Now, temperature also can affect the properties and behaviors of matters through our physical changes and our phase changes, or our transitions from one state to another. So, thinking back to all the ways our substance can change, remember we either lost or gained heat to make a transition from one state to another, and we wrote it on our diagram. So, if we're going from solid to a liquid, we're gaining energy and we're going to be melting. If we do the reverse, we're going to be losing energy and we'll be freezing. So, we'll keep these transitions in mind as we talk about a phase diagram in this video. Now, if we're going from a gas to a liquid, we'll have condensation. And if we go from a liquid to a gas, we'll have evaporation. Remember, evaporation can go under the broad term of vaporization, but that also includes boiling with it too. And then our new changes that we might not have heard before, going from a solid straight to a gas, is something that's subliming or sublimation. And then a gas to a solid is going to be called deposition, aka depositing our solid from a gas. Now, these are all phase changes, and remember, they're all physical changes, meaning that we're not going to be changing the identity if we undergo any of these changes. What we start with is what we end with for it. So if we're talking about a phase diagram, and we can see our phase diagram right here, we'll see it's just a graphical representation of the physical states of any substance. So each substance has its own unique phase diagram for it. Now they're all set up the same way, but we'll notice that some of the lines shift depending on what their state of matter is at room temperature, and then how it changes with pressure and temperature. Now, a typical phase diagram has our pressure on the y-axis. So remember that our y is going down, and we'll see that we have pressure there. And we're going to see that our temperature is on our x-axis. So remember our x going across for it. Now, pressure can be measured in ATM, mmHg, torr, or kPa, and we'll see that temperature is usually measured in degrees Celsius or the absolute scale of Kelvin. Now, you'll notice that we have a range of our solid, our liquid, and our gas here. They have a definite border, aka this dark line that separates them, and you can see that they use different colors to show those different regions. Now, as we cross the lines or the curve that we see over here, we're going to see that a phase change occurs. So if we transition from our solid to a liquid, at this point we're all solid, at this point we're all liquid, but as we cross over that line, we're going to see that we now transition from our solid to our liquid. And you'll see the reverse for freezing. Now remember, vaporization is just a broad term for evaporation for it too. Now that's our phase diagram. It plots out our solid, our liquid, and gas, and then it shows us in the regions where freezing, melting, vaporization, aka evaporation, condensation, sublimation, and deposition occur. So we saw there's transformations between two states of matter at a time. Do you think there's a point where all three can exist at once? Now, if you were looking on the graph before, you might have saw that there was this thing called the triple point. And the triple point is special. It's right in the middle of our graph, but you'll actually see that it's easy to spot the triple point because all three states of matter, or all three of the colors, actually meet at the triple point. That means that they would be at equilibrium, all there at the same time. So that means we would have a solid, a liquid, and a gas at this small point, aka the triple point, or where all three states of matter meet. Now, we can actually find the exact pressure by going over to the y-axis and plotting it. Notice there's no numbers on this diagram. And we can also find the exact temperature for our triple point there. So that's a pretty cool point. Our triple point, triple meaning three, all existing at once. And a lot of times you'll just see on diagrams, I write TP for it, not toilet paper, triple point. So another feature of the phase diagram is going to be something known as the critical point, aka our CP. Now, our critical point is right at the top of the line between our liquid and our gas. And this critical point shows that there are no more boundaries between our liquid or gas slash vapor. So I'm even going to add that to my phase diagram right there. So after the critical point, you cannot distinguish between a liquid and a gas. And we actually call this region, so we would say this region over here is known as a supercritical fluid. And a supercritical fluid is special because after that pressure and temperature of the supercritical fluid, it can effuse through solids like a gas, but it can also dissolve materials like a liquid. Supercritical fluids are usually at very high temperatures and very high pressures. So it takes a lot of work to get to that supercritical fluid for it. So those are the two major points that we can see. Now remember, we can also plot out our melting and freezing point. We can plot out our boiling point if we're looking between our liquid and our vapor too. So let's answer some questions about this water phase diagram. So it even has our title of our phase diagram. We notice that we have our temperature on our X and we have our pressure in ATM on our Y. So we notice that we have our solid. So I'm going to label it S. I have my liquid and I have my gas vapor. We can see we have our triple point right in here and we have a critical point all in here, meaning that anything after it would be that supercritical fluid. So what would the pressure be for the triple point of water? So we found our triple point right here, and I'm going to change to a highlighter. So we have here, and we're going to see that the pressure for the triple point would be 0.00604 for it. Okay, we could also find the temperature, which says that the triple point would be 0.01. It didn't ask for it, it only asked for pressure. Now, what does it mean to be a normal freezing or boiling point? So this takes us back to last week's lesson. So to be normal, we're going to see that it has to be at standard pressure. So what we're going to see is the standard pressure for this is at 1. So notice that it's already labeled as normal freezing point and normal boiling point. So that means that at that standard pressure, we can tell from our phase diagram what its normal freezing slash melting point is because they're at the same point, and then what our normal boiling point is. Okay, what is the temperature for the critical point? So I'm going to switch back to a highlighter. I find my critical point. Remember, temperature's going down. And we're going to see that the temperature for my critical point is 373.99 degrees C. Okay, our last one. What phase change occurs when you go from liquid to gas? So we're crossing this line right here. Let me change my color. So we're crossing this line right here. We're going from our L to our G. You might not need your graph there, but we wouldn't say it's boiling. We could say that it's vaporizing or evaporation would be occurring. Okay, so really what this phase diagram does, it combines all the lessons that we had separately on our solid, our liquids, and our gases and puts it in one easy diagram. Now remember, the diagram changes for whatever element compound you have. The only thing that won't change is what we have here. Your solid will always be closest to your X, your liquid's always in the middle, and then your gas is always on the bottom. So thanks for watching about phase diagrams, and have a great day.